I'm sure you guys are wondering why I strapped a motor to the front of my truck. Obviously, I wanted more power. Turbo mode. No, I'm not strapping this to the front of the truck to make the truck go faster. Oh, that's an interesting idea. No, in this video, I'm going to show how I characterize my motor and propeller combination for thrust at speed. Motors, propellers, and the airspeed for an aircraft all have to be matched to work together. And you can't do that with this strapped to the bench. You guys see me do that testing before, and you can only go so far. So I hacked my $40 scale and turned it into a thrust measurement system. Up to 600 volts.
Motor repair, take one. These 4 bolts here.
That shaft moves this lever. It's alive! I already did a bunch of static thrust testing. You probably saw that in my other videos. This is all about dynamic thrusting. So in this video, I'm going to show you how I hacked apart my refrigerant scale to get an accurate thrust and drag data for my propeller and motor combination for installation on the electric ultralight. I went through several iterations on this testing. It took a lot longer than I had planned to get good data. First I started off with a pretty small load cell and a linear bearing, and the idea of the linear bearing was to on a long pole, I got that 4 feet or so in front of the truck, so I get clean free stream air, and I didn't have to react to any odd loads in the load cell with the linear bearings. Used this simple 20-pound load cell. I spent a lot more time than I had originally planned playing around with getting an Arduino jack set up. The actual recording of data wasn't the problem, it was just getting everything to work together. So a couple of proto boards I made up so I could record all the data stream from the VESCs, battery current, motor current, voltage, ERPM, temperatures, etc., as well as a load cell reader and a GPS chip so that I could record actual ground speed and record the strain directly. Now I've got my Arduino recording to the SD card. It takes GPS, position, altitude, time, speed, which is the big one that I want out of it, and it also records the force gauge, but I need to calibrate the force gauge. The best way I have is my accurate scale that I have over here. It's actually used for charging refrigerant systems. They're a very, very accurate scale, and you can pick them up for cheap. And so I'm starting it off with the horizontal position. There should be essentially no load, so this will be the tare position. So turn that on. I'm going to get a few data points, and while I'm going through, I'm going to record. Oh, for weighing, I actually have this 52-pound Bowflex weight set, which are really nice. But it has an additional feature. Take that off. And now I've got a nice set of plates. To the 0 tare position afterwards. 7.53 pounds. So I'll go ahead and put that on. So I ended up doing a bunch of load cell testing here, and unfortunately I never got results that I liked between the accuracy and the precision. I don't know if that was due to the linear bearing I was using, the cheap load cell, or the HX711 load cell amplifier. I spent a lot of time with this. I wasn't getting the satisfactory result that I wanted. and reached the point where I just had spent more time than I had wanted to, and kind of just ended up dropping it. I have the static thrust stand, and I'm going to take it out. It's just a scale. It's actually a very accurate scale made for weighing refrigerant, but I'm going to take it out so we can use it for the thrust rig. Alright, so I tore apart the CPS refrigerant charge scale and was pleasantly surprised. So I bought this off of eBay a few years ago, I don't know, 40, 50 bucks, somewhere around there, used. And so got some really nice parts into it. So we'll start with the most important part, or one of them, which is the load cell. So this is actually what measures the force that's being applied. Under here, potted under this, is the strain gauges. Nice CNC machined piece of aluminum. This is not just extruded, it's actually fully machined on all sides. And I went on HPM's website. They make really good strain gauges. Unfortunately, they don't have any documentation for this CC101. It was obviously specifically made for this company, and so that's why there's not public information on it, or at least either that or it's older. But it's actually made in 2014. Assuming that's what that number means. So anyway, it's 110 kilogram, which is more than enough load capacity for me, with a 50% safe limit before you actually, what that limit is, before you actually would bend this and yield the aluminum. So yeah, this beam load cell here was well worth it just for the $40. Digging further into deeper, so the 4 wires here return the strain readings, and it gets converted over to the signal here. I was hoping to dig into this board, but it's gonna keep all of its secrets from me, and so I really don't want to tear that open. But that is what's actually converts that strain reading into the actual force reading. So I've actually playing around with extending the wires here. I couldn't find the connector, but it's just at a 2.54 millimeter pitch. So I just took some ribbon cable, and I'm actually going to cut here, splice in some foam cable to get the length I need. From there, it runs to the readouts there, but from there, it sends the information to the handheld. Anyway, yeah, for 40 bucks for essentially a really accurate handheld load cell. Maybe it's 50 bucks, but really happy with it. The only thing I just wish I had data recording, but I will just have to write it down. Alright, so this is the 20 kilogram cheap load cell that I was trying to use, and I'm going to replace it with the one from the scale. Now I could just splice it in and just use the load cell, but I want this nice accurate Wheatstone bridge here that converts the strain readings into a real force reading. So that goes out, that goes in. So I have my load cell, and I needed to mount it to the 80/20 frame that I already had. So of course I go into the junk pile and pull out some random pieces of aluminum and made out a motor mount so I could swap motors very quickly. Alright, let me walk you through the test setup here before I get into the details. Originally, I made this frame up out of 80/20. Actually had it left over from another project. They were going to throw it away and recycle it, so I got it, so it's just scrap material. Originally, I was actually going to plug in as a trailer hitch behind the license plate there, but I was going to plug it into there, but I wanted a nice wide mounting frame there so that this is like one with the truck. There's no flex in there whatsoever. Okay, there's very little flex there. So anyway, 80/20 mounts to the hard point, so I can take this off and I can put my high lift and my shackles back on and go up the mountains, which actually I'm gonna do tomorrow, now that I think about it. So anyway, got this wire here. This runs to the load cell in the truck. You can see it hanging right there. These wires are the 3-phase that run the brushless DC motor. Those run to the ESC, which is also in there. I ran the ESC in the truck because I actually wanted to duplicate the long run of cable that I'll have through the wing spars and so this is a more representative installation to my installation. So anyway, that goes with the ESC. I got data logging in there, and I was worried about shielding because the motors up front here obviously put out some electromagnetic interference, or can potentially, since they are electromagnets, pretty strong ones too. So originally I was going to run shielded Cat5. That's all this is Cat5 cable. I didn't actually have any on me, so while I did order some, I got impatient and just wired it up. And then I actually had this copper tape. I would just use aluminum tape, but I happen to have copper tape laying around, and what else are you going to use it for? So then it goes through here, it goes to the load cell. So load cell, I won't do a big explanation of what it is, but essentially it's a set of strain gauges that measure the deflection, that very accurately measure how much this moves. And the way this is made is specifically designed such that the force that you apply here has a direct relation to the amount of strain that comes out. So, and the way this beam load cell is set up is such that it's rather independent of exact loading direction. It's just going to measure the force that's going in that direction. Mounted a scrap piece of aluminum to that, and then I split it such that I can get this A shorter, but then to change out motors, I can just loosen these 4 bolts and take it out. Also, if I want to pull off the whole setup, I can just take off these 2 screws, and then the whole thing just slides off and I can take it inside. Then I got the motor and the propeller, and that's pretty much the this test setup there. So let's go get some more data. It's actually a lot of fun getting on the road with this thing. It's kind of a unique experience having this thing sticking, I don't know, 5 feet out in front of the truck. But the looks you got from people driving down the road were pretty interesting. We'd start recording with it just freewheeling to get the drag of the prop, but then I would hit the power and get different levels. One of the things you don't need to worry about when you are in a wind tunnel is traffic and stop signs and wind. So that made it a little bit more challenging, and had to do some laps around the neighborhood. Luckily, I have some streets that don't have a lot of traffic on it and are fairly straight. So we just waited till the day that there wasn't much wind. Did do one day of testing where it was there was windy, and we just did it with made sure that we were perpendicular to the airflow, and that worked okay. But the data was really noisy, and it was hard to get a steady state out of that because of that large crosswind component. Occasionally we have to pull off to the side. I would check and make sure that the load actually go back to 0, that I'm getting a good tear. Also recheck the static thrust. Just doing those kind of repeated data points at periodic intervals, just to make sure that I was getting the quality and repeatability of data that I wanted. One of the challenges is actually just maintaining constant speed. We live up kind of in the hills, so we've got hills up and down. And ironically, an electric vehicle would have been much better vehicle to do this testing, because you can hold your speed much better than a truck with a V8 and a transmission shifting, etc. But it ended up working out well. The other thing is obviously stopping for traffic, but yeah, it's the things you accept for not having to have a 4-foot diameter wind tunnel. The testing did was not just testing under power, but also interesting. Some of the first tests I did was actually with it freewheeling, and I did test with the propeller locked, so it wasn't spinning, as well with the propeller free spinning, because I wanted to characterize how much drag I would be having with the power off. So just kind of lather, rinse, repeat. We would hold the current constant, and then go up to speed, sit there for a long enough time to be able to get a steady state, and then move to the next data point, and had all this lined out. I went started at 15 miles an hour and then went in 5-mile per hour increments all the way up to 65 miles an hour. And I swapped out for the next prop. This one had to be carbon fiber, again same profile. I did 3 different props, all the same diameter and profile, just different pitch. I had done all that static thrust testing where I tested a dozen different motors and propellers, and it was easy to do that at the bench. use that to down select so I could really focus the time that it takes to do the dynamic testing with these 3 props. I was hoping to have a little computer record all of the data, and there's actually, I think, a serial connection between the handheld and the Wheatstone bridge. Didn't want to spend any more time in the software world, so I just went old school with handwritten data cards. The way I would do this is, I tried it several different ways, but what I found the best way for getting good data was I would hold the current constant. So you go into the VESC, you can program a maximum current level, and then we just run up the speed. So start at 0, verify that I'm getting the right static thrust. This is always a good check, just compared to the bench anyway. Got really good correlation, so I wasn't really concerned. The checks I did, I made it so I wasn't concerned about any modifications I made by taking this out and potential interference. I really took care of that issue. And then I would just increase the speed, 0, 15, 25, 30 miles an hour, all the way up to 65. That's the speed regime that I'm concerned about for the airplane. And yeah, it worked out really well. The computer was still recording all the other data. I had the GoPro recording, and we just hold a constant speed. Easier said than done on roads with traffic and a big truck, but it worked out well. Obviously did it on a day where there was no wind because I'm measuring the speedometer. Both we have GPS and the speedometer on the truck records ground speed. What I'm really concerned about is airspeed. So you got to make sure that the wind is little to none so that you're not affecting the data. But went through that, did quite a few of the data points on it, and again compared that to the static thrust data that I had done on the bench, and yeah, was able to make some really good comparisons on the motor. Have to laugh. My daughter was very insistent that she sat in the back of the truck, and she was being my little flight engineer, and she actually, I'm not kidding, this is all her idea, writing down numbers furiously as I yelled out forces and currents, which, you know, put a big smile on my face. Numbers! High five for numbers. So with that, what did the data say? So I took all that data and all those test cards that I wrote things down and just inserted them into Excel. That fun job of data reduction. Here's the first chart that I threw together. This is one prop, 26 by 16, with the constant propeller or a constant motor, and where I kept the current constant and then just varied the speed. There's a lot of different ways you could do this. This is the one that I thought would be the most best for people to be able to absorb. Think of for these motors, constant current is roughly analogous to constant torque. I have a torque sensor. I didn't put it on. The analogous of the motor current is pretty close. So if you think this is constant torque, you look in the static thrust testing. This is what I've done before. Well, obviously more torque will give you more RPM, and that'll give you more thrust. The whole point of doing this testing, though, is that thrust is not constant for speed. As you go faster, the pitch of the propeller really comes in, and the thrust will drop off with speed. Unless your propeller is stalled because the angle of attack is too high at static thrust, then you will end up seeing this this thrust drop off. But even with that, so the thrust drops off with speed, and because I want to be able to make sure that I can actually cruise the airplane at a sufficient margin, so I don't want to have, where if I had the wrong pitch of propeller, I could have great static thrust and really take off very quickly, but then I wouldn't be able to go more than, say, like 30 miles an hour. But if my stall speed is at 25, then if you have a power issue or whatnot, that's not a safe place to operate an airplane. So as you can see, I did this. I also did it for 0 amps. So I did go through And I actually did some testing just out of curiosity if I fixed the propeller versus if I had the propeller freewheeling. Not a big surprise that the delta between these two is actually quite small. A lot of people argue about, not a lot of people, but pedantic people will argue about whether if the propeller is fixed and not spinning or if it is freewheeling, which has less drag, and will, in case you have an engine out situation, what's safer? A, you don't usually have much control over that, but B, really the reason why I think there's so much argument is that it's fairly small impact, and it's not really a critical function. So as you can see here, the fixed propeller is lower in drag, so this is measuring drag since it's a negative force, and the freewheeling propeller was pretty much higher at all points. There's a plate across, which I thought was, or they touched at least, but really the fixed propeller is better, but it's honestly a pretty small impact. I also went through and figured out thrust required. Really simple calculation. Just took some wags. The CD knot. I don't have drag data for this airplane. I thought about strapping to a trailer, and at some point I just have to stop taking data and get back to building the airplane. So. Came up with the prediction of the thrust required. This thrust required does not include the effects of my distributed electric propulsion. So, because I get a higher CL while blowing over the wing. But anyway, came up with the curve from that, and the whole point of that is so that I can overlay these. So, we'll jump to this. Well, we'll jump to this guy here. So these are all the tests that I had done. As you can see, the different lines are different currents and propeller combinations. The motor was held constant, and I can have a cruise speed. So I can go faster with the higher. I get much higher thrust, but I'm really pushing the motors too hard, and they will be overheating. 35 amps are what they were actually rated at, and I've actually been impressed with these T-motor motors. Is that they have a lot of data on their website, which is really refreshing, just compared to most of the Chinese motor manufacturers, which have maybe a number, and you probably can't trust that one. Here I found their data actually and their published values to be quite believable. So 35 amps is the rating on these motors for a continuous operation. I think they test for 3 minutes. I've tested for longer. 30 to 35 amps is that rate range. Obviously, it depends on ambient conditions. If it's hot outside, you can't reject that heat as well. But so that gives me, with my picked CD knot of 0.08, which is a fairly high one, but a right flyer is 0.1. I should be able to cruise somewhere in the 55 mile per hour range. Obviously, an interesting note at that cruise power, they all actually kind of coalesce there. So kind of for that cruise power, I actually have the same amount or relatively same cruise speed, regardless of which prop that I picked. The bigger difference you notice will come when you get to the higher current levels. So this is 50 amps. So constant motor, constant current, but just changing out the propellers. The 26 by 10, as saw on the static thrust testing, that gives me the highest static thrust. But you can see that these all decreasing, and they're decreasing at different rates, and they actually end up crossing here. So if I were designing an airplane that I wanted to cruise at 80 miles an hour, and I wasn't going to go faster than 65 on public roads. That's not safe. And don't really want to get the family arrested just for the sake of data. But so 65 miles an hour is as fast as I had gone getting data. But you can extrapolate this out. You can see the gray curve is that 10 pitch prop, and that's going to drop off pretty significantly. But if you look at the green, it starts lower, but it crosses, and it's staying flat all the way up, from 65 miles an hour. So, where this drops off, I'd have to get more data points. I wouldn't be able to assume what it is. But if I were wanted to cruise at 65 or 70 miles an hour, or potentially faster, then this 26 by 16 is where I wanted to be. And the 26 by 12, I didn't have a 26 by 14. That would have been nice to have another set of data points, but these are the props that I had. Again, they were the same manufacturer, the same profile, and there was a difference in material, but the profiles were supposed to be the same per the manufacturer. So, but as you can see, I went with the 26 by 10 prop because I wanted that static thrust. Going back to my chart here on cruise at 35 amps, I'm not going to go more than 55 miles an hour anyway. It is an ultralight. There is a limitation on how fast I can actually cruise, and so I wanted the best margin in the regime that I was looking at. I'm not going to go faster than 60 miles an hour, so the fact that this is dropping off here and would probably continue down if I had gone faster really isn't a concern. So that was the whole point of doing this testing, is I wanted to know what pitch to pick. There are some rules of thumb and guidelines but the ways that the methods that are used to select the pitch, along with the airfoil that are used in the propeller, the amount of twist that's put into it as it goes to the root, etc. All those things make it really hard to predict, and all you get is some rules of thumb. Those rules of thumb said I should have been at the 26 by 16. And it would have worked out right. It was fine for I think I picked a 60 mile an hour cruise. But all of those are clustered right in there. Now look, but if you extrapolate back that I really want more thrust at low speed, I essentially get that for free. I might as well pick the ideal prop for my speed regime, and in that case, it's a 26 by 10. Now, a 26 by 8, would that have been better? I might have got, I don't have one of those. I didn't want to buy yet more props. I think I've bought about a dozen props over this project. And it probably would have been higher static thrusts, potentially, and then it would have probably fallen off even faster. So while this starts to dip below here, maybe it's another 5 miles an hour faster. But it's hard to speculate. That's the whole point of doing testing data, is that getting this data is you don't have to. So there we go. That's the characterization I did on the motors and propellers. It's kind of a challenging thing from a testing data standpoint, because the motor has a torque curve for a given RPM and given current and voltage that it needs to see, or that has, and then the propeller has a curve that is torque and thrust and airspeed, and all of those things need to be matched to the aircraft. So this was something I've always wanted to do, a fun test, and had fun doing it, but I'm really looking forward to getting back to working on the airplane. So yeah, I mean, other thing I want to mention was voltage. So I actually use the same battery and same length of wires that I'll actually use on the airplane, same gauge, so I had the right voltage drop. I didn't start with a completely fully charged battery. I actually had the battery midway charged because I knew that I would only have that kind of voltage at the very beginning of the flight, and I wanted to characterize what it's going to seem. If you really want to see in real flight, if you really wanted to be conservative, you would actually have a almost dead battery. But then and if you had a constant power supply that you could tune that to, then that would work as well. But that's going to change over time. The voltage is critical because the RPM is limited by the back EMF, and so you have to be able to overcome that voltage to be able to drive the current to get to the RPMs. So if this motor is a 12S motor, I'm using a 12S battery. As that decreases, the RPM will actually decrease slightly with that voltage. But so anyway, don't do the testing with the best case, most ideal situation, because the real life application is only going to be worse than that. Try to be conservative on your input. But yeah, I got all the data and down selected the props, so I now have 11, maybe 10 now. No, 11 carbon fiber Zor props. I wanted to get this all characterized before I went and spent $600 on props, and of course I ordered one extra because things always happen. But yeah, and I can't wait to get these onto the airplane and start doing some ground testing. So let's get these on the airplane. That'll be the next video. Will be me installing the motor mounts, talking about the static testing for it, the wiring, running the wires through the wing, drilling, installing props. I actually made up my own drill jig because these props aren't designed to go on that motor, so I had to make up my own drill jig to get all that installed. But you'll have to stay tuned for that in the next video.